So now that we're finished with chapter 13 and discussing some of those functional groups like epoxides, ethers, alcohols, how they react, how they form, we're going to talk a little bit more about carbon bonds again, and particularly double bonds. But this time we're not just talking about the standard single double bond. Excuse the awkward phrase there, but now what we're going to talk about is dienes, specifically conjugated dienes, but we have to become familiar with other types of dienes as well. So there are three types of dienes that you need to be familiar with and be able to identify in the structures. And these are simplified examples. So you can also find them in rings, going in and out of a ring. The definitions we'll see in a moment is really based on where the double bonds are located relative to each other in a chain, regardless of if there's cyclic structures around or not. The main idea is if the two double bonds both share the same, or at least share one of their carbons is the same carbon, and that is to say, these two double bonds, they both emanate from this carbon right here that's being represented by this dot. You could also draw the letter C to represent that carbon. So there's a double bond from this carbon going over to the neighboring carbon to the right, and then there's another double bond going to the left. When it's connected on the same carbon like that, it's called cumulated. And it's actually it's one of it's the least stable of these three structures. Then you have just two regular double bonds that happen to be in the same molecule, but they're not close enough to have any kind of special property, either destabilizing or stabilizing. And so we call those isolated. And that's essentially if there's two double bonds in a molecule that is separated by at least one sp3 carbon. So right here, this carbon right here, it has two hydrogens coming off of it. If you envision it with your bond line vision and can see them, there's two hydrogens there. And so this is an sp3 carbon right here. So that the presence of at least one between them means those two double bonds, that diene is isolated. It's an isolated diene. The two double bonds are isolated from each other. And then this structure right here is an example of what we're really going to talk about mostly in lecture, the reactivity of at least, and that is conjugated dienes. Conjugated dienes are when the two double bonds are essentially separated not by any number of carbons that are sp3, but rather they are separated by a single sigma bond. There's the only thing separating these two double bonds is a sigma bond. They don't share a carbon. That is to say, like the cumulated, they don't share one of the carbons that are part of the double bond aren't shared between the two double bonds. They each have their own two sets of carbons, but you know, one sp2 carbon on one of the double bonds is sigma bonded to the sp2 carbon on the other one. So that's a conjugated diene. And then this is just showing the pi orbitals of those pi bonds that make up the double bond. So in the accumulated, they're perpendicular to each other and they have no interaction with each other. Whereas in the conjugated system, right here, they are perfectly lined up, very much like when we talked about resonance and anions and cations back in organic chemistry 1. So they're perfectly lined up, and that's what's called conjugation. We talked about that when we talked about resonance. And then finally, if you look at the isolated, as you can see, so in the conjugated, the four p orbitals are all perfectly in line with each other and are able to mix with each other and overlap, creating an extended bonding space. Whereas the isolated, they're just two regular double bonds. Now, it doesn't have to be carbons, all of them. You can have heteroatoms, that is to say, atoms that are not carbon, like oxygen or nitrogen, be part of the conjugated system. So the pi bond can be connected to a non-carbon atom, and the system is still considered conjugated. So this is a conjugated enone. The En for the double bond, the one for the ketone. And then here we've got a nitrogen that's double bonded to a carbon. So, how do we make conjugated dienes? Well, fortunately, as we're going to talk about in a second, they're actually more stable than even isolated dienes, and definitely more stable than cumulated dienes. And so there's a favorability um, to their preparation or synthesis. The one thing we do have to watch out for is starting, assuming you already have an alkene here, and then you have a good leaving group at the allylic site. It turns out the allylic carbon, um, because of the resonance that can exist, if this were to fall off and create a carbocation, and there would be resonance with it, stabilizing it, that makes this carbon really susceptible to a nucleophilic attack. So remember when we learned last semester that nucleophilicity tends to line up with the base strength. In other words, good nucleophiles tend to be strong bases, or at least strong bases tend to be also strong nucleophiles. We need to avoid any substitution occurring. So usually, to ensure the synthesis of conjugated dienes, especially when you're starting with a good leaving group at the allylic site, you need to use a sterically hindered strong base. That way, it's not tempted to act as a nucleophile and cause substitution. So, terp butoxide is always our good go to sterically hindered base. And so, even when you have two good leaving groups right next to each other, using a sterically hindered base will favor the deprotonation from the N carbon here and from the N carbon here, also generating the conjugated diene. One thing just to point about the bond lengths is the conjugated dienes have a much shorter sigma bond that separates them than a regular alkane. And the reason for that is the sigma bond between two conjugated dienes is made up, the sigma bond, of two sp2 hybrid orbitals overlapping. So these carbons are sp2 hybridized, so the two orbitals that overlap to form the sigma bond are two sp2 hybrid orbitals. So why does that matter? Well, something we talked about last semester, particularly with ARIO, the way to determine whether how stable something is for acid-base chemistry. When you look at sp3, sp2, sp orbitals, you can easily say that sp3 has much less s character in it as a hybrid orbital than sp2, which has less um, s character in it than an sp orbital, because they're essentially mixing together those orbitals, an s and a p, so it's 50% s. An s and two p orbitals leads to 33, or in other words, one third of it is s character, and mixing an s orbital with three p orbitals means three of the four orbitals are p's and one of them is an s, 25%. So why does that matter? Well, think of an s orbital as being closely held to the nucleus compared to p orbitals that are stretched out like a dumbbell. The more s character that something has, the shorter that orbital is. And so sp2 orbitals, when they overlap, are much shorter, so they have a much closer overlap rather than the sp3 orbitals that are what are normally overlapping in alkanes. So that explains the shorter bond length for the sigma bonds in these conjugated dienes. What about the stabilization? Well, how do we even know that they are more stabilized? Well, one of our common go-tos, and we're going to use this again when we look at aromaticity. The common go-to to determine whether, to compare two different things and to see how stabilized a structure is compared to something else, is oftentimes to find some reaction or set of reactions that cause the two compounds we want to compare to end up at the same product. If it's ending up as the same product, then the only thing that would cause a difference in energy for that reaction would be the energy of the starting material. In other words, the fact that they both turn into this exact same structure here, why is it when you react 2 moles of hydrogen with this diene, it only releases 239 kilojoules, whereas when you react 2 moles of hydrogen gas with 2 moles of this single diene, or the single double bond in um, in that molecule there, why is it more energy is released? You would think, if there is nothing special about conjugation, that if you have twice the double bonds, you should release twice the energy of a single double bond undergoing this hydrogenation reaction, but you release a little bit less. So why is that? Because the reason why that is that two pi bonds conjugated in the same molecule is slightly more stable than two double bonds that are not conjugated, or even if they're in two different molecules. So the fact that these two pi bonds are in the same molecule and conjugated leads to a 15 kilojoule lower energy for this structure. In other words, it's lower in energy, so it's closer in energy to the fully saturated alkane. So that is why less energy is released, because it's not, excuse me, it's not as unstable as two molecules with a single double bond. So, how do we use this to our knowledge? Well, we've learned several things throughout the year and last semester about stability of double bonds and stabilities of structures in generals. So we look at these three structures here. They look mostly the same. There's several differences in them. First of all, compound A has only two double bonds, whereas the other ones have three double bonds. And one thing that we did realize, notice we're talking about two of these molecules undergoing hydrogenation. In other words, this energy, 254 kilojoules, is being released for two of these, meaning a single hydrogenation event actually only released half of this. So really, it's probably somewhere around here. So a single double bond in a molecule is more stable than two double bonds in a molecule, even if they're conjugated. So this molecule, one of them, is actually more stable than this molecule that has two double bonds in it. So the number of double bonds, the more double bonds you have in a molecule, um, the more unstable that molecule is. However, when the molecule has the same number of double bonds, then you have to think about other things. So let's take a look at what the order of this is. So the correct order of energy for these compounds, and the question is saying rank them in the order of increasing stability. So A is the most stable, and that's because it only has two double bonds in it. Then comes a D. D is the most stable, followed by B, and lastly, C is the least stable. So why is that? Why is D the most stable of the three that have three double bonds in it? Well, that's because look at this. It has three, or I should say, all three of its double bonds are conjugated together. All of them together are conjugated because each double bond is separated only by one sigma bond to the next. So that extended conjugation makes D the most stable of the three compounds with three double bonds. Now, what is the most stable between these two? Or why is B more stable than C? Well, let's take a look at their double bonds. First of all, sterics sometimes is an issue, but as we can see, um, all of these issues, all of these compounds roughly have the same nature. Most of them they're very similar in their E versus Z or cis trans nature. There's no real difference in that because they're part of a ring structure. The one thing that is different is the substitution. And what we mean by substitution, back in chapter, I believe it was 8, when we first learned, no, I think it was 7, because it's where we made double alkenes for the 1st time. We learned about substitution. In other words, when the double bond has carbons instead of hydrogens connected to the double bonded carbons. And what we learned last semester, was tetra-substituted alkenes are more stable than tri-substituted are more stable than di, and di-substituted are more stable than mono-substituted. And so look at these compounds. Here you've got a double bond that is di-substituted. It has two carbons connected to it. Here you have a double bond that is tri-substituted. One, two, three of the four things connected to the two double bonded carbons are carbons. And here you have a di-substituted. So you've got two di-substituted and a tri-substituted. Whereas in compound B, you have this double bond, which is tetra-substituted. All of the groups that are dangling off the double bond are carbons. Here, this one is tri-substituted. Three of the things connected to the double bonded carbons are carbons, and this one is di. So you've got a di, tri, and tetra. This one you have a di, and tri. So more of the double bonds in compound B are more substituted alkenes than in compound C. Conjugation isn't a factor between these two. In both of these, two of the three double bonds are conjugated with each other. And then the other one is isolated, separated by more than one sigma bond from the other double bonds. So they have the same conjugation, but their substitution is different. And by the way, these are numbered in order of significance. In other words, first and foremost, the less double bonds you have in the molecule, the more stable that molecule is, the lower the potential energy. Then, if you realize there is no difference in the number of double bonds between compounds, then you look to the conjugation. If the conjugation is the same amount, there's no difference, then you look at the substitution. And then if on the rare chance the substitution is exactly the same for all the double bonds in the molecule, lastly, you look at sterics and see if there's any difference. If some of the double bonds are cis versus trans or Z versus E. Remember, trans and E double bonds are more stable than cis because of sterics. And speaking of sterics, we'll end with the video. And that is the sterics of the sigma bond, which is a little weird because usually, like we learned last semester in OChem 1, we learned that sigma bonds usually rotate freely because there's nothing that holds them like the overlap of the p orbital holds the or prevents the rotation, but along the bond between these two carbons in a double bond. You can't rotate that because you would break the overlap of the p orbitals. Why is it that there's some hindrance in the rotation of this sigma bond? The reason is because this is a conjugated diene, there actually is overlap of p orbitals in these molecules. In other words, whether you're in the S cis or S trans state, in both of those two examples, all of the p orbitals are overlapping each other, whether they're cis or whether they're trans. Cis, whether they're trans. The p orbitals are overlapping as is shown in this diagram. So this is the plane. So let's take a look at the energetics then of rotating about the sigma bond. So first of all, the S cis configuration of a conjugated diene is less stable than the S trans. And that's because of sterics. These two groups right here, these two end carbons are right next to each other, and that repels, there's repulsions that these feel with each other, whereas they're far apart from each other here. So that's why this S trans form of the conjugated diene is more stable than the S cis configuration. And The conjugated diene can rotate between the two, but there is a little bit of an activation barrier that they have to get over. There's a little bit of a hindrance, um, or at least it requires a little bit of energy. So if the system gets too cold, you may not find that they flip around too much. They get kind of locked in place. Why is there this barrier? Look at the value, 15 kilojoules per mole. What did we see already that was 15 kilojoules per mole? Oops. 15 kilojoules per mole was the stabilization energy of the presence of conjugation. And it makes sense that that would be the barrier of the rotation going from S cis to S trans, because in order to go between these two configurations, you have to rotate that sigma bond. And as you rotate it, you're going to go through a state in which these two p orbitals are still overlapping each other. These two p orbitals are still overlapping each other on the other double bond. But because you've rotated that sigma bond in the middle, you no longer have all four of them overlapping each other like you do when you're either in the S cis or the S trans. So, in order to go between those two states that have the conjugation, you have to go through a state where you've broken the conjugation. The two separate uh, double bonds are still double bonded. The p orbitals of those two carbons with each other, each of those two sets of carbons, they're still overlapped. These two are still overlapped with each other, and these two, but the total overlap of all four of them has been broken as you rotate that middle sigma bond. And so that breaks the conjugation. And so that causes a 15 kilojoule increase in energy of the system as you break the conjugation, because the presence of the conjugation represented a 15 kilojoule stabilization. So I believe that's it. I don't want to make these videos too long, and that's really a good thing to just kind of give you that this video for you to watch about um, some of these fundamentals of conjugated dienes, some terminology, a little bit about the energetics. I know you'll probably still have questions because it never really sinks in the first time about the whole, you know, hydrogenation, demonstrates the stabilization, and we're going to use that again for, as I said earlier, aromaticity. So please ask me questions in lecture. I'll give some time at the beginning on Tuesday when we go over this topic of conjugated dienes to address some of the confusion you may still have about the proof that conjugation leads to more stable dienes, and maybe we'll be able to talk it through a little bit and understand it a little better. And also, please continue to read your textbook. Don't just rely on lecture and even these videos. The whole point of the whole reason why people used to lecture in academia in the 1800s and the 1900s was because books were hard to come by, and so we were the purveyors, professors of knowledge. But now there's people who write textbooks who create wonderful little tomes of knowledge. um, Now the role of the professorship, I feel at least, is to help you work through and clarify these things. At least I try, and I know I can be not always perfect in my explanations. So please, if you're confused, always ask a clarifying question. Lay it out for me. Help me understand what's confusing. Besides my speech, confusing still. Anyways, I'll see you in lecture for conjugated dienes and their reactions.